Welcome to lecture 18 of Natural Language Processing Theory and Applications. So in the last couple of lectures, we had discussed the transformer, a neural network architecture that is widely used in NLP. So we discussed the architecture in fair amount of detail, and we also discussed some characteristics of the transformer. So, and in particular, we basically discussed the type of transformer which is used for as a causal language model or autoregressive language model. So today we will extend that and talk about bidirectional transformers, transformers that can attend to information both on the left hand side as well as the right hand side of the current position. So previously we had talked about the causal transformer or left to right transformer in which every position I would only attend to information that appeared before it. And we, of course, used it for language modeling, and it can also be used for other applications as well. But now we will extend it to bidirectional attention, and that particular case is called a bidirectional transformer. So that would be the agenda for today. And I think after this lecture, we will be focusing more on some applications that use both of these models. Uh, so because these models, as I said, are used widely in almost all applications, and we'll see how they can be adapted for various applications. So let me share the screen. So are there any questions? Any questions? So as I said, we will talk about the bidirectional transformer today. And in particular, we'll talk about the model that's called BERT, bidirectional encoding representation with transformers. This was proposed in 2018 from Google. So 2019. And in particular, the language model that is used or that is developed using this model is called what is called as a masked language model. And we will see what this means today. So I will use the slides for a while, and then we'll also go to the notes. Okay, so this is actually chapter 10 of your textbook. So previously we discussed the transformer, which was in chapter 8. So we have kind of skipped chapter 9 for now. We'll come back to that later on. So in the previous chapter or the previous lecture, we have talked about the causal language model or the left to right language model. And we discussed the transformer in that context. In that particular case, uh, every position that we were concerned with, let's say the ith position in the sequence of words or tokens, that position attended to all positions that appeared before it developed its representation. So that position, as it went through various transformer blocks, attended to representation that appeared before it, and at the end of all the blocks, the hi that you got at the end of the last block was a representation for the ith token that also took in information from the preceding tokens. So that was uh, useful for applications in which you wanted to predict the next token. So let's say you're looking at the ith token, and once you have that representation at the end of the last block, you can use that to predict the word that would appear at the next level or I plus one by putting a language head at the end of that representation. So we discussed this last time. So that was the autoregressive or left to right or causal language model. But of course, and this particular model was also called a decoder. So why was it called a decoder? Because we considered information in sequence, one step at a time. So when we were at the ith position, we considered all the preceding information, and using that information, we were able to uh, use it to predict the next information or next token. And you can do this repeatedly sequentially. So this process of repeating processing and trying to predict the next is called decoding. And this model was as such called a decoder. So in contrast, the model that we talk about today is an encoder. So again, it's a transformer, but you will get a representation that is not necessarily used to predict the next word, and it can be used to predict the information for that particular token only or the entire sequence. So this is generally called an encoder. All right, so let's look at the basic architecture. So how does the bidirectional, the key difference, as I said, is that uh, we attend to both the left-hand side as well as the right-hand side at any given position I, instead of just what has appeared before a position I. So that's why this is called bidirectional. So if you talk about any, so this figure basically shows you an input from x1 to x5. These may be tokens, input embeddings for those tokens. So if you consider, if you look at the left figure, that is the causal language model. So in that case, for any particular position, let's say x3, so x3 का जो output होगा a3 and or h3 at the end of the entire transformer blocks would only contain information of x1, x2, and x3. While in the case of a bidirectional transformer, the H3, that is the output that appears corresponding to the input X3, would contain information for all the inputs X1, X2, X3, X4, and X5. In other words, it is taking information, or the attention goes to the left-hand side as well as to the right-hand side, and of course to itself as well. So that is the key difference between the two. And of course, uh, as you know from language, a particular word का जो मीनिंग है या syntactic या semantic meaning है, it depends on the words that appear before it as well as after it. So in that sense, this representation is richer than the autoregressive or the causal representation that we saw in the previous uh, chapter or in the previous lectures. But of course, these have slightly different applications than the ones that we saw for earlier on. All right. So how do we do this? Uh, as the slide says, this is quite easy. Actually, we had already discussed the causal transformer. The only change that you will need to make is to remove the mask matrix M that we introduced when we were discussing the uh, the model for the causal transformer. Or in other words, the mass that we used for that was kind of putting minus infinity to the matrix that we got after we computed the scores. So if I want to write those equations again, so if you recall, the attentions as a matrix for all the inputs x1 to xn as rows in this matrix A, capital A, is basically given by row-wise softmax of uh, of the matrix multiplications of q k transpose divided by sqrt of dk plus m. M was the mass that we used previously. And the purpose of the mass was to ensure that the matrix that we had in the previous term, which is q k transpose t divided by that, we kind of ensured that the higher values in that matrix became minus infinity. The values in the upper triangle became minus infinity through this mask by adding this mask. So in other words, this mask M had values of 0 for the lower triangle, including the diagonal, and had values of minus infinity above the diagonal. So that when you add it to the previous matrix, you get a matrix with minus infinity in the upper diagonal. And once you take the softmax, each row would then have values of 0 beyond that. ठीक है? Of zeros beyond that. I think we used the term alpha for this before in the last lecture. A नहीं था. So alpha is actually the alpha scores, weighing scores, attention scores that we had. So the alpha is again a matrix. Sorry, alpha is now as a vector. ठीक है? If you multiply this with V, then you get the A matrix, which is attention output for each head or for each input AI. ठीक है? But in this case, now in our case, so this is for the causal transformer. ठीक है? You simply remove the mask. That's it. So the matrix multiplication Q, K transpose T already computes the attention to all the terms, all the tokens in the input. So in the previous case, they were already computed. We then kind of subdued that by adding a mask to it. But now we have removed the mask, then you actually get a bidirectional transformer. Okay? So this alpha, then of course, from this you get the A's, the capital A, which is the output of each input AI, each input Xi from the attention mechanism, as basically the previous thing, which is alpha, into the matrix V. So the matrix V is the matrix of the values for each of the inputs Xi. Okay? So this is how the attention mechanism would change in the bidirectional case. So as you see, the change in terms of mathematics is kind of trivial, just removing the matrix, mass matrix M. And the A's that you get, all the attention outputs that you get for each of the corresponding inputs are in the matrix capital A, are given in the same way. And then of course, the rest of the transformer blocks remains the same. So BERT, bidirectional transformer and causal transformer are the same except for this change. Okay? So as if you recall, हमारा जो transformer था वो क्या था? Input थी हमारे पास. Then we had block 1. Then we have 2 dash 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 2 block block L, and then you have, for example, the language head or output layer. सो अगेन आपका जो बाई डायरेक्शनल ट्रांसफार्मर है उसका भी आर्किटेक्चर यही है. विद इन ईच ट्रांसफार्मर ब्लॉक you have your layer norms, you have the multi-header tension, you have the feed-forward layer, and the output of each transformer block goes to the next transformer block and to the next transformer block and to the last transformer block, and then from that to the output layer or the in this case the language head. तो बाकी चीज़ें ठीक चेंज सेम है. टेंशन मैकेनिज्म में मास्क निकाल देते हैं एंड वी गेट द बाई डायरेक्शनल ट्रांसफार्मर. एनी क्वेश्चंस? So the first model of this kind was BERT, which I said was proposed in 2018, 2019 by people from Google. So, so basically this model had a vocabulary size of about 30,000. It had 12 blocks. Each block, the multi-head attentions, there were 12 multi-head attentions. The input context length was 512 tokens, and the model dimension was 768. Okay, model dimension is what? The dimension D that we talked about earlier. कि embedding का size क्या है, attention जो AI आता है हमारे पास output उसका भी वही size होता है, HI का भी वही size होता है. Remember we said that we try to make the transformer as modular as possible by ensuring that these dimensions are the same, so that एक output दूसरे output के अंदर feed हो सकती है. The original, of course, use different tokenizers, word piece, sentence piece, and so on. BPE usually नहीं था, but BPE भी use कर सकते हैं आप. So total number of parameters in this model was 110 million, 110 million. ठीक है. So ये नंबर ऑफ पैरामीटर्स के लिए मैंने एक स्लाइड बनाई है. आई वांटेड टू शो यू कि वो एग्जैक्ट किस तरह निकालते हैं. ठीक है. So let me move to the next slide. And by the way, this calculation, while it is done for BERT, it would be the same for any transformer, including the transformer that we saw in the previous lectures, which were causal transformers. तो दोनों में पैरामीटर वाइज कोई चेंज नहीं है. तो मास्क जो हमने ऐड या रिमूव किया तो वो पैरामीटर नहीं था, इट वाज कांस्टेंट. ठीक है. सो लेट मी स्टार्ट दिस स्लाइड. So BERT, of course, has various variants. We will specifically talk about the variant which is called the base variant. So we have already talked about this. Oops, 201 तो नहीं है, 219 है. By the way, actually, I prepared a first draft for this from GPT, and you can use, as I said, GPT in this course. But उसमें कुछ errors थे जो मैंने कुछ ठीक भी किए हैं. ये वाला 2001 वाला भी रह गया. अच्छा, so we have 12 blocks, transformer blocks. So 768 is the side model dimension, which is the size of the embedding, the size of the token embedding, the position embedding, and so on, the size of the attention output, and so on. So we have 12 attention heads within each block. The feed-forward layer, which has two weight matrices, as you know, the size of the hidden layer is usually 4 times the model dimension. So in this case, it's 3072. So vocabulary size, subwords, it's not complete words, subwords is over 30,000. And context size is the input, the total number of input tokens that it can take, which is 512. Okay? So where do the parameters come from? And so there are two main sources of parameters. One are the embedding. So usually in most large language models, the embeddings that we start with for each token are also adaptable. ठीक है? So embedding layer को कहते हैं previous chapters में even in the back in the feed forward neural network आप embedding layer include कर सकते हैं. Transformers में भी include कर सकते हैं. We mentioned it briefly previously as well. So जो embeddings matrix E है वो आपका parameter matrix होता है. वो आप while you are doing the learning you can update that as well. Of course you started with using the static embeddings maybe like word to vec, but बाद में इसको आप through the training process update भी कर सकते हैं. ठीक है? So as such they become parameters. So embedding layer parameters हैं and then ट्रांसफॉर्मर ब्लॉक्स के जो पैरामीटर्स हैं. एंड ट्रांसफॉर्मर ब्लॉक्स में आपको पता है कि कई चीज़ें हैं उसमें. फीड फॉरवर्ड लेयर है, टेंशन मैकेनिज्म है, लेयर नॉर्म्स हैं. ठीक है? Let's see the computations in the next slide. So we talk about the embedding parameters. So there are actually multiple types of embeddings as we have already seen, and there's one new addition that you see in this slide. I'll talk about that shortly. So there's a token embedding. So this is the embedding that is for each word or subword in your vocabulary. And this can be derived from word piece, sentiments, sentence piece, or BPE algorithm as we saw earlier. Sorry, and the tokenization can be done by that. And of course, the static embeddings can be drawn from word to vec. ठीक है? सो टोकन एम्बेडिंग्स हमारे पास कितने टोकन थे इस मॉडल में? ओवर 30,000. एंड ईच टोकन का साइज, जो एम्बेडिंग का साइज, जो मॉडल साइज है वो 768 है. So basically we'll have to multiply the vocabulary size by 768 and that would be the token embedding. So position embedding क्या थी? There was a embedding for each position in the input stream. So हमारे पास कितनी input stream थी? There were 512 input positions. And each embedding की size वही होगी जो model size है because we later on add them up. ठीक है? Size वही होगा unless they if you don't keep the same size they cannot be added. So 512 into 768. And in BERT in particular, as we'll see later today, BERT में sometimes हम दो मल्टीपल सेगमेंट्स ऑफ इनपुट दे सकते हैं. उन सेगमेंट्स को आपने डिस्टिंग्विश करना है तो आपके पास सेगमेंट एम्बेडिंग भी आप बना सकते हैं. तो जितने भी सेगमेंट्स होंगे उतनी एम्बेडिंग्स होंगी. सो यूजली देयर टू सेगमेंट्स, एक ए एंड बी है तो बेसिकली 2 टाइम्स 768 ये एक और एम्बेडिंग. एंड ऑफ कोर्स ऑल दीज थ्री एम्बेडिंग्स वुड गेट एडेड अप एट द स्टार्ट टू द फर्स्ट ट्रांसफॉर्मर ब्लॉक. And then of course there's a layer norm after this, and there's a layer norm in there are two layer norms in the transformer block, and there's a layer norm after the embedding layer. So layer norm may I didn't mention this in class, but in the book you can look up in the detail. Layer norm, as I said, is done by G-score normalization. But G-score normalization को slightly parameterize भी कर सकते हैं with two parameters for each position. ठीक है? तो हमारे पास पोजीशंस कितनी है एम्बेडिंग्स की, हर एक एम्बेडिंग की 768। सो 2 टाइम्स 768 आपके पास ये लेयर नॉर्म की पैरामीटर्स आ गए। तो gamma plus beta parameter in the z-score normalization approach for layer normalization। ठीक है, तो ये आपकी एम्बेडिंग लेयर की सारी पैरामीटर्स आ गए, जिसमें प्राइमरीली आपके पास टोकन एम्बेडिंग्स हैं। ऑफ कोर्स ट्रांसफार्मर में फिर पोजीशन एम्बेडिंग्स भी होती हैं, और बर्ट में बाई डायरेक्शनल में सेगमेंट एम्बेडिंग्स भी हैं। ऑफ कोर्स सेगमेंट एम्बेडिंग बहुत छोटी है, दो ही हैं सिर्फ। तो टोटल आप करेंगे तो यू गेट 24 मिलियन। तो अप्रॉक्सीमेटली 24 मिलियन एम्बेडिंग्स आपकी पैरामीटर्स हो गए एम्बेडिंग लेयर की। So let's move on to the transformer block. So each layer or each block of the transformer contains the multi-head attention mechanism, the layer norm, and the feed-forward mechanism. तो मल्टी हेड अटेंशन मैकेनिज्म में आपके पास चार मेट्रिसेस होती हैं, के सॉरी डब्ल्यू के डब्ल्यू वी एंड डब्ल्यू ओ, फॉर क्वेरी की वैल्यू एंड आउटपुट। So these matrices are in general D times dk for WQ and WK, and D times dV for WV, and WO would depend on the size of your these the size of, basically you are concatenating all the 12 uh, आपके पास जो हैं, and basically W output जो है ना वो concatenation के बाद अप्लाई होता है to give you one final embedding of the same size as the original D। ठीक है, तो इन दिस केस एक्चुअली ये सारे डब्ल्यूज जो हैं इनकी डायमेंशंस डी के भी डी है, डी वी भी डी है। तो वी कैन इजिली कंप्यूट देयर साइजेस। ठीक है, सो डब्ल्यू का 3 टाइम्स 768 टाइम्स 768, डब्ल्यू ओ भी 768 टाइम्स 768। ठीक है, तो यू यूजुअली ऑल्सो हैव ए बायस टर्म विद these मेट्रिसेस जो हमने डेफिनेशंस में हमने जो इक्वेशंस लिखी थी उसमें ऐड नहीं किया। ऑफ कोर्स दिस इज ऑप्शनल, बट यूजली हम डू ऐड करते हैं प्रैक्टिस में। बायस सिंपली ये होता है कि जब भी अब हम लीनियर प्रोजेक्शन करेंगे प्लस एक वेक्टर ऐड कर देंगे, या सिंपली उस वेट मैट्रिसेस में एक पहला कॉलम ऐड कर देंगे ऑफ बायस वैल्यूज। ठीक है, एंड ऑफ कोर्स देयर साइज इज नॉट वेरी लार्ज, इक्वल टू 768। सो 4 टाइम्स 768। ठीक है, चार मैट्रिसेस है, चारों में 768 साइज का बायस की वैल्यूज भी ऐड कर दी, वेक्टर्स हैं ये। ठीक है, तो ये हमारे पास डब्ल्यूज की सारे आगे वैल्यू, बट दिस इज फॉर जस्ट वन अटेंशन हेड। ठीक है, तो आप इसको 12 हमने मल्टीप्लाई करना है, वो बाद में हम करेंगे। तो लेट्स मूव ऑन टू द फीड फॉरवर्ड। तो फीड फॉरवर्ड नेटवर्क में दो मेट्रिसेस हैं, उनके साइजेस यहाँ दिए हुए हैं, बिकॉज मिडल लेयर का 3072 है। तो पहला 762/3072 होगा, दूसरा 3072/762 होगा। इन अदर वर्ड 2 टाइम्स बोथ ऑफ दीज वैल्यूज, प्लस ऑफ कोर्स है बायस, बायस ऑफ कोर्स दोनों का डिफरेंट होगा। सेकंड लेयर का 3072 होगा, फर्स्ट का 768 होगा। ठीक है, बायसेस आपके दो आते हैं। ठीक है, सो हम ये वाली स्लाइड और पिछली स्लाइड ऐड कर दें तो ये है 7.1 मिलियन पैरामीटर्स। ठीक है, which means that one transformer block has approximately 7.1 million parameters। बट बर्ट बेस में 12 ट्रांसफार्मर ब्लॉक्स हैं. सो वी ऐड देम अप. ठीक है, ईच लेयर में 7.1 है, 12 है. सो 85.2 million parameters for all the transformer blocks. ठीक है. बाय द वे, इसमें जो लेयर नॉर्म के जो पैरामीटर्स है ना, वो एम्बेडिंग्स के साथ डाली हुई थी. यू कैन इंक्लूड इट इन द ट्रांसफार्मर ब्लॉक ऑल्सो. ठीक है, इन अदर केस वही वाले पैरामीटर्स इधर भी हैं. तो कैटेगराइजेशन आप अपनी मर्जी से कर सकते हैं, थर्ड बिग इशू, बट वहाँ काउंट हुए में. सो ये हमारे पास 85 ये हैं, 24 वो हैं, एंड देन इफ यू ऐड देम अप, विच इज इन नेक्स्ट स्लाइड. समरी आगे, एक सेकेंड. तो दोनों को ऐड करें तो ऑलमोस्ट 109, एंड इन द लिटरेचर यू सी ए वैल्यू ऑफ अबाउट 109 110 मिलियन. ठीक है. सो इन अदर वर्ड्स, सो दिस इज हाउ यू एस्टिमेट द नंबर ऑफ पैरामीटर्स इन ए लार्ज लैंग्वेज मॉडल बेस्ड ऑन ए ट्रांसफॉर्मर. ठीक है. यू ब्रेक इट डाउन इनटू टू मेजर कंपोनेंट्स. एक एम्बेडिंग पैरामीटर्स होते हैं, और एक ट्रांसफार्मर जो इंटरनल्स हैं उसके पैरामीटर्स होते हैं. यू डू इट विद इन द ट्रांसफार्मर ब्लॉक. देयर आर मल्टीपल कंपोनेंट्स, सारों को निकालें, मल्टीप्लाई टोटल नंबर ऑफ ट्रांसफार्मर ब्लॉक्स एंड सो ऑन, एंड ऐड इट अप. ठीक है. सो I wanted to go over this in bit more detail so that it would be clearer to you कि parameters आ कहाँ से रहे हैं. And again, it's kind of a refresher for the architecture of a transformer, the architecture of a transformer. आपको पता लग रहा है कौन कौन से components हैं और किस तरह काम चल रहा है. Any questions? Okay. So coming back to our bidirectional transformer or BERT. So we have seen its architecture. The architecture is identical to the causal transformer except for the removal of the mask. ठीक है. Now, the question now is, how do you train this model? And originally it was meant for language modeling, and the particular type of language modeling that is done using this type of architecture is called a masked language model. Okay? The previous one was simply called the language model. This one is called a masked language model. अब उसको we understand that by looking at how it is trained. So in the causal transformer or the causal language model, we were given a sequence, and we were given that sequence, that was the context. We were use that context to predict the next word, and then we can use it repeatedly to generate text. So that was what we did for the causal transformer model. In this case, in the case of bidirectional, we will try to predict a particular word given the word that appear around it, a central word. Okay? Okay? So So given any input sequence like this, we will we will kind of mask a randomly selected word, and then try to predict that word from the context that appears left and right of that word. Okay? So again, it's a prediction problem over the entire vocabulary. But now we are not doing it at the end of a stream by considering only the preceding words, but now we are doing it at within a particular word within the stream by considering both the left and right hand side. And if you recall, word to vec में जो हमारा context था, जो word to vec में हम यूज करते थे, वो भी context both left and right था. उसी से ही हमारे पास embeddings अच्छी आती थी, right? And embeddings were what? They were representations for words. So here again वही idea use कर रहे हैं. We consider a word and the words that before it come before it after it to develop a representation for it. ठीक है, so let's look at a bit more detail. So how do we do this? So remember, this is self supervision. आपके पास input text है, input text is running text. कोई भी आपका 512 tokens आपने लिए running text में, उसमें 15% या of course in the entire training data 15% of the tokens आपने मास्क कर दिए, नॉट ऑल बट 15%. ठीक है, अब जो मास्क आपने किया या आपने जो सिलेक्ट किए हैं उसमें से वी डू ए फर्दर क्लासिफिकेशन कि जो हमने सेलेक्ट 15% किए हैं उनमें से 80% ऑफ द टाइम वी रिप्लेस दैट विद ए न्यू टोकन कॉल्ड मास्क. एक नया टोकन हम डिफाइन कर लेते हैं मास्क. वी कैन गिव इट एनी वैल्यू लाइक ऑल जीरोज और ऑल माइनस वंस और ऑल पॉइंट फाइव्स. एक नया टोकन हमने डिफाइन कर लिया विद एम्बेडिंग ऑफ ऑल जीरोज और ऑल माइनस पॉइंट वट एवर. ठीक है, रैंडमली आप जनरेट करके एक टोकन बना लें. इन अदर वर्ड ये टोकन बताएगा सिस्टम को कि ये हमारे पास वर्ड मास्क हुआ हुआ है. ठीक है, सो इफ यू हैव दिस सेंटेंस, सो तो लेट्स से 15% हमने चूज करना, तो लेट्स से डिलीशियस वाज चोजन. सो द थ्री पॉसिबिलिटीज एज आई सेड, 80% ऑफ द टाइम हम डिलीशियस को मास से रिप्लेस कर देंगे, द स्पेशल टोजन मास्क. सो लंच फॉर डिलीशियस को लंच वाज मास्क, एक टोकन मास्क कर देंगे हम. सो इन अदर वर्ड आपका जो इनपुट जाएगा बर्ड को फॉर ट्रेनिंग में, उसमें ये जाएगा लंच वाज मास्क, नॉट लंच वाज क्या कहते हैं डिलीशियस. Of course, this is the case when you replace it with mask. But there are two other cases. एक केस में 10% of the time, 80% of course mask कर रहे हैं, 10% of the time वही word रहने देते हैं आप delicious, और 10% of the time some randomly some other word, मतलब some error add कर रहे हैं. ठीक है, let's say you replace it with gaps. ठीक है, ठीक है. Of course, again repeating it, वहाँ पर complete training data set है, पूरी corpus है. First of all 15% words हम पहले select कर लेते हैं. अब एक वर्ड लेट्स से डिलीशियस सेलेक्ट हो गया. नाउ वी डू अनदर रैंडम प्रोसेस. अब डिलीशन में 80% ऑफ टाइम वी विल बी एबल टू यूज मास देयर. 80% में वो नहीं आया तो दे रैंडमली मे बी 10% ऑफ टाइम उसको वही डिलीशियस रहने दिया, या रैंडमली 10% ऑफ टाइम वी अगेन जनरेट ए रैंडम यूनिफॉर्म रैंडमली सेलेक्ट एनी अदर वर्ड. इन दिस केस एग्जाम्पल लेट्स से गैस. तो आपने ट्रेनिंग डेटा को इस तरह पहले प्रोसेस कर लेना. तो आपके ट्रेनिंग डेटा में फिर आपके पास मास्क होंगे किसी जगह पे, किसी जगह पे वही वर्ड होगा, किसी जगह पे कोई रैंडमली अदर वर्ड होगा. सो इन अदर वर्ड यू काइंड ऑफ created a noisy training data, and now you will train it using this and force the network to learn the original data, the original token, the original word. ठीक है, So this is now showing the complete bidirectional transformer model. So for those 15% tokens that are masked, that are selected, of course, some of them will be masked, some of them would be the same word, some of them would be changed to other word. तो उनका जो आउटपुट होगा उसके हम ऊपर क्रॉस एंट्रोपी लॉस निकालेंगे. ऑफ कोर्स मास से हमने प्रिडिक्ट करना है एक्चुअल वर्ड डिलीशियस प्रिडिक्ट करना है. गैस पे भी हमने डिलीशियस प्रिडिक्ट करना है. ऑफ कोर्स जब डिलीशियस है, डिलीशियस और डिलीशियस प्रिडिक्ट करने पे कोई एरर नहीं होगा. ठीक है. So in other words, ये process हमने क्यों किया, इसने divide क्यों किया? Why did we have a mass there and then we have this and that, one with the original word, one with the random? So we wanted, because when जब इस model को बाद में use करेंगे, in the actual case, we won't have any mass token there. We'll have the actual word there. ठीक है? जो actual word, then for that one we would like to get the representation for it. ठीक है? So in the training we would like to force a representation, and to force the representation we start with a mask token, and of course in some cases we start with the error token, and to let the model it might be correct as well, एक delete correct token भी हमने रखा हुआ है. So this is the reasoning why we do this kind of division. So the final layer से जो आपके पास output आएगी for the word that has been selected, उस पे loss develop होगा. वो loss of course आप you will do it, add it up for let's say number of batches of training, and then you use that loss to backpropagate into the network and update the parameters. Okay? And of course, that updating process, as we said, we have not gone into detail, but essentially it's backpropagation. Okay? ठीक है. So हम आपके पास input corpus है, उसमें सिर्फ 15% of the words have been selected. So remember, 85% of the words have not been selected. So the model will only get trained by those 15% of the words that are selected. So in that way, the training of BERT is relatively slower as compared to a traditional feed-forward neural network or even a causal transformer. Because उसमें सारे words participate नहीं कर रहे in training. Only those 15% words that we had selected were participating in the training, and उन 15 में से भी जो mass वाले थे और जो error वाले थे वो error generate करेंगे. जो 10% वो वाले थे जिनमें वही word use किया तो वो error generate नहीं करेंगे. So as such, ये slower learning process है. Okay. So, so the original BERT actually used two tasks for training the model or learning the parameters. One task was the mass language model, which we just discussed, in which we took a corpus and then randomly selected some words for masking and then fed it into the model and then used it to predict the masked word. So in other words, kind of a denoising process कर रहे हैं, उस denoising process आप उसको model को learn कर. But ये सिर्फ एक टास्क था. ओरिजिनल बर्ट में एक और टास्क से भी लर्न करने की कोशिश की थी, विच इज कॉल्ड द नेक्स्ट सेंटेंस प्रिडिक्शन टास्क. ठीक है. सो दैट्स द वन दैट गोइंग टू गो टू नेक्स्ट. So you take a corpus as before. Remember, all of this is self supervision. कोई external supervision की जरूरत नहीं है. Supervision is already available in the data. ठीक है. You take a corpus और उसको आप segments में divide कर दें, या more appropriately sentences आपके पास already available है. एक sentence है, दूसरा sentence है. In this case, the task is we want to predict if We give two sentences if the second sentence immediately follows the first sentence or not. ठीक है. Again sentences क्या है? Sequence of tokens है. Next sentence sequence of token है. ठीक है. And we want to predict whether the second sentence, let's say B, follows the first sentence A. So it's kind of a binary classification problem or two class classification problem. It's not a vocabulary classification problem, but उसमें input आपके tokens ही जा रहे हैं. So to model this, BERT used added additional tokens into the input stream. इसमें जो tokens हैं वो एक CLS token है, which is added at the start of both sentences. ठीक है. Then we have sentence A, उसके सारे tokens, और फिर उसके बाद एक SCP separated token है. That tells the model कि ये पहला sentence खत्म हो गया, उसके बाद दूसरा अब शुरू होगा. फिर second sentence B आ गया, उसके सारे tokens हैं. फिर finally एक और SCP token है, which is a separated token again. So in addition to this, they also had to tell the model कि कौन सा पहला sentence है, कौन सा second sentence है. So in other words, जो हमने embedding position embeddings की बात की थी, this is by the way, it's not really a token, it's kind of an embedding, या आप attention mechanism के अंदर इसको include कर दें. But you can use it as embedding. जैसे हमने embedding की calculation में देखा था, तो you need to calculate a embedding that tells us that this is the first sentence and this is the second sentence. So पूरे जो A के जो tokens हैं, A sentence हैं, उसके जो tokens हैं, उसमें first segment का token add हो जाएगा और सारे जो B के tokens हैं, उसमें second segment का tokens add हो जाएंगे. To tell the model that this is second sentence. ठीक है. So these segment embeddings are added to the token as well as the position embeddings at the start of the transformer. So जो CLS token है, it's a token at the start of the sequence. अब again remember this is a bidirectional attention mechanism. CLS token start में है, बाकी सारे tokens बाद में. Attention सारी CLS को भी आ रही है. इसका मतलब CLS has seen all the subsequent tokens, including the separated tokens. So CLS token has all the information of the two sentences. So जो CLS token के आगे फिर आप एक classification head लगा सकते हैं. उस classification head में simply you have two outputs, tell you whether the second sentence follows the first sentence, meaning yes or no, 1 or 0. Binary classification कर रहे हैं. So this point clear? So in other words, let me तो आपके पास एक CLS टोकन है शुरू में. तो लेट्स से कोई आपके पास कोई सेंटेंस है. तो फॉर एग्जांपल कैंसिल माय फ्लाइट्स, ये स्लाइड्स पे भी था. ठीक है. फिर सेप है एंड द होटल एंड सेप. ठीक है. तो आपकी इनपुट स्ट्रीम ये होगी. सो इन दिस पर्टिकुलर केस द सेकंड सेंटेंस एंड कैंसिल माय and the hotel is a correct follow-up sentence to the first sentence. So in other words, let's say जो हमने ट्रेनिंग डेटा में दिया तो इसका CLS टोकन के आगे जो आउटपुट लेंगे वो हम yes लेंगे. So the second sentence is a true follow-up to the first sentence. ठीक है. So let's say मेरे पास कोई और इनपुट होती है इस तरह की, जैसे CLS cancel my flights, SEP he lives in Lahore, for example. So in this case, he lives in Lahore is not a follow-up sentence to the first sentence, and in this case CLS का जो token है उसको हम output 0 देंगे. या आउटपुट जीरो लेने की कोशिश करेंगे. So what is the idea here? Again, we are trying to train the model to learn these words, learn the tokens such that it can understand similarities, it can understand differences, and in general get a better representation for each token. So दो टास्क एक ही लर्निंग प्रोसेस में यूज हो रहा है. एक मैक्स मास लैंग्वेज मॉडल टास्क यूज कर रहे हैं और एक नेक्स्ट सेंटेंस प्रिडिक्शन टास्क. So एक मास लैंग्वेज prediction and then the next sentence prediction task. So two tasks are used to train the model. Of course, the original BERT में था, some variants of later on of this used only one, meaning the mass language model only, not the next sentence prediction. ठीक है? So this is the entire model with some input that was fed into the model. ठीक है, तो ये वही वाला एग्जांपल है, cancel my flights and then and the hotel as well. ठीक है, तो आपका मॉडल essentially ये बनेगा. So these are details on more details on the original model. So 40 passes over the entire data. So why were those 40 passes needed? Because the training was relatively slow. Multiple passes देने पड़ते हैं, especially for MLM, because 15% of the words are uh, selected for training purposes at any point in time. So that would uh, result in slower trainings of the model, and that's also another reason why उन्होंने NSP भी इसके साथ ऐड किया हुआ था. So remember दो टास्क लिए, मार्क्स लैंग्वेज मॉडलिंग भी और नेक्स्ट सेंटेंस प्रिडिक्शन भी, दोनों ने यूज किए टुगेदर. As I said before, some model do not use NSP, for example Roberta. So for multilingual modeling, you get tokens from all the different languages, and then you'd have data from all those languages. If you have a few languages, generally the model becomes better. But if you have large number of languages, unless your model is very large, then you run into problems. So these are some empirical results that people have found. So basically, the curse of multilinguality. बहुत ज़्यादा आप languages ले लें, then the model is not able to learn properly, especially if the model is small and the data is small. ठीक है? So, so all right. So this was the training. By the way, इस training में again from your training data set आपने 50% of the time next sentence follow up sentence लेना है, 50% of the time next sentence randomly some other sentence लेना है, so that your model has options of equal number of options of ones and zeros, yes or no. ठीक है? And again this is self supervision, कोई external labeling annotation नहीं चाहिए. Just as we saw for word to vec, just as we saw for causal language modeling, for mass language modeling, and for now for next sentence prediction. And this is actually one of the key, you can say, uh, key strengths of NLP and many other tasks, even in data science, for example, where you can use this approach to learn representations for different entities. In this case, we are learning representations for words without requiring external annotations. ठीक है. So let's any questions? So let's say you have trained the model using both MLM and NSP on a large amount of data of a particular language or multiple languages for that matter. Once you have a trained bidirectional model, whenever you give it a new sentence, meaning that आपको नया टोकन इसको दें, तो हर टोकन का एट द एंड ऑफ द ब्लॉक HI जो आउटपुट आएगी वो एक रिप्रेजेंटेशन उस टोकन की होगी. That representation now would be a contextual representation, meaning that it is a representation based on what has appeared before that word and what has appeared after that word. ठीक है? So if you remember हमने ये इसकी discussion पहले भी की थी. So for example, the word bank is a polysemous word. ठीक है? So उसमें for example, if you used word to vec, bank की एक ही embedding होगी. That's a static embedding. But if you have bank in different contexts, its embedding should change. Let's say मैं एक sentence लिखता हूँ, they picnic on the bank and he met the bank manager. ठीक है? So both of them are bank, but दोनों बैंक का जो embedding है, if you use word to vec, वो एक ही embedding देगा, which hopefully would contain both contexts, both meanings, but whenever we are doing an application, एक word एक ही context में या एक ही meaning या एक ही sense में use हो रहा होता है. So if you already have a pre-trained BERT model, what you will do is you will feed this sentence into BERT. पहला वाला sentence feed करेंगे, they picnic on the bank. जो बैंक का जो output होगा after the model, HI जो बैंक का आएगा, you can use that as a contextual embedding for bank. और later application में आप वो use कर सकते हैं. So that would now become a contextual embedding. And that would be more strongly tied to the concept of bank being a river bank or a lake bank or so on. On the other hand, if you send the second sentence into that trained model, उसमें बैंक की जो embedding आएगी, जो final representation आएगी, वो would be more tailored towards the idea of a bank being a financial institution. ठीक है? So in other words, so you can use BERT, for example, to get contextual embeddings. ठीक है? And once you have obtained this contextual embeddings, you can use it for whatever you want to use it for. So similarly, remember BERT में जो एक और जो second setting होती है वो आपके पास CLS है, and then you have a sentence. ठीक है? So he lives in Lahore, for example. ठीक है? अब if you feed this into a pre-trained BERT और CLS token का आप embedding ले लें, तो that would be an embedding for this complete sentence. By the way, ये sentence नहीं हो सकता, बड़ा भी हो सकता है, depending on how much long context आपका network ले सकता है. So this would give you a sentence embedding. CLS will give the sentence embedding. ठीक है? So once you have a pre-trained model, and there are many that are available out there, simply feed it a new sentence और उसका CLS token का जो output है, जो HI है CLS का, that you can use it as an embedding or representation for this complete sequence of tokens or a sentence. ठीक है? So remember हम previously जब हम word to vec discuss कर रहे थे, हम कह रहे थे कि sentence का representation किस तरह निकालेंगे. We talked about a number of techniques. We said we can do averaging, for example. We can do min, we can max pooling, and so on. Now you get a representation directly from the model that is much more, hopefully much better than simple averaging or min or max pooling. मिन तो नहीं होगा, यूजली मैक्स पुलिंग होता है। ठीक है। So contextual embeddings can be obtained from a trained bidirectional language model by feeding into it the text that you want to process and obtaining the representations at the end of the model. We have already talked about this. ठीक है, so of course if the word आपका बैंक किसी और कॉन्टेक्स्ट में आ रहा है या कोई और वर्ड किसी और कॉन्टेक्स्ट में आ रहा है, उसकी एम्बेडिंग डिफरेंट हो जाएगी. So मेरे ख्याल से I probably skip these slides. You already know this. Uh, so a word can have multiple senses, and a particular sense of a word is most appropriately determined by the context in which it appears. And that context is not defined by just by the preceding word, but may also contain the next words. And a bidirectional model can be used to determine the representation for that word. And then based on that representation, you can determine how similar two words are. ठीक है. और फैक्ट लेट्स से आप सेंटेंसेस की आप निकाल रहे हैं प्रेजेंटेशन, तो दो सेंटेंसेस को भी आप कंपेयर कर सकते हैं. ठीक है. ऑलराइट. So basically, you should go over these slides. ये कोई इसमें कोई नई चीज नहीं. We have already discussed this word sense. By the way, I can mention this word sense disambiguation is so word sense disambiguation is a traditional NLP task. This task is concerned with determining the particular sense in which a particular word has been, uh, ha- the, or you, in other words, determining whether uh, two words have the same senses or different senses, or determining the sense in which a particular word is used in. और ये ट्रेडिशनली एनएलपी में ये बहुत इंपॉर्टेंट टास्क था. अब ये इतना रेलिवेंट नहीं है बिकॉज यूजली इट इज not the end goal of any application. It's maybe a part of an application, but that is usually handled internally by the transformers. But let's say आपके पास कोई इसका similar task आता है, you can get representations from your BERT, for example, and then do cosine similarity or nearest neighbor match or any other approach to find uh, embeddings that are similar, which would tell us that these two words have the same sense, or if they are different, then they have different senses. Okay, now let's briefly talk about applications. And before that, I will briefly talk about transfer learning. And this is a general concept that is applicable in machine learning and also to neural networks in the context of machine learning. So far, so we talked about language modeling when we discussed the causal transformer, and we also talked about language modeling when we discussed the bidirectional transformer. Okay? And in particular, the mass language modeling. And those models were pre-trained on large amounts of data, and the process was primarily self-supervision. Okay? So you have a huge amount of data, you train the model on some task, usually MLM or NSP and or causal language modeling, to learn the parameters of the model. So now you have a model with all the parameters learned, and those parameters would capture the nuances of the languages over which it has been trained. Nuances of the tokens, the syntax, the semantics, the discourse, the pragmatics, and so on. सारी चीजें in a way it would be able to capture. But if you want to reuse it, this model in a slightly different domain, then we will have to do what is known as fine tuning. Okay? So fine tuning meaning basically means that adapt the model for new task. Remember original task क्या था? Language modeling था. New task कुछ और हो सकता है. And adapting, of course, can mean different things. And in this particular case, primarily we'll be updating the parameters. Okay? So, so let's take the example of, let's say, a classification problem. So let's say specific example sentiment classification कर लेते हैं. ठीक है? You already have a pre-trained model, a BERT model. How can you use it to do sentiment classification? So so simply आपके पास नया ट्रेनिंग डेटा होना चाहिए. ठीक है? Meaning that you should have sentences or documents and their labels. So documents and labels data होगा आपके पास. ठीक है? So you will input that document into your BERT model and you like to predict the label for it and adapt the model accordingly. So how would you do that? Input को आप इस तरह process करेंगे CLS and document tokens. ठीक है? So let's say for example आपके पास है CLS, the movie was great. So obviously this is a plus positive example. So आप ये नेटवर्क के अंदर फीड करेंगे, जो CLS का जो रिप्रेजेंटेशन आएगी उसके आगे एक आप क्लासिफिकेशन हेड लगाएंगे और उस हेड को आप फिर उसका आउटपुट फोर्स करेंगे टू 1 using this data. Your model has already been trained on the MLM and NSP task, but now you remove the last layer, which was a language modeling head, and replace with a new classification head and retrain it on your own data. But usually we will not retrain the entire model. We will only adapt the last language model. So usually not adapt the entire model, but just the last classification head. ठीक है? So आपके पास जो आउटपुट CLS की आएगी वो आप क्लासिफिकेशन हेड से गुजारेंगे और force it to the new data set, which is your sentiment classification data set. So if you give a positive example, आपका loss 1 और 0 के साथ आप करेंगे और सिर्फ उसी हेड को अडाप्ट करेंगे, not the entire model. Although you can do that, but that's going to be very costly. Okay? So in this way, you can basically do what is known as sequence classification. Okay, so it could be any problem: sentiment classification, document topic classification, email spam classification, emotion classification, sarcasm classification, gender identification. So all of this can be done by simply feeding the text and taking the output of the CLS token, passing it through a classification head that you have adapted to your own training data set. So this part, if you do this, is called fine tuning a pre-trained model. And in a way, we are doing transfer learning. My original learning था for NSP and MLM, mass language modeling. उसका knowledge हमने transfer कर दिया to sentiment classification or to spam classification or to some other thing. ठीक है? Okay. So another category of applications is basically uh, so for example, so this is another category, but there are various applications in this. For example, paraphrase detection. For example, uh, next sentence prediction. ठीक है. नेक्स्ट सेंटेंस प्रिडिक्शन हो सकता है, पैराफ्रेज डिटेक्शन हो सकता है, एंटेलमेंट आइडेंटिफिकेशन एंड सो ऑन. सो एसेंशियली इन दिस केस वही वाला हमारा जो एनएसपी का आपका टास्क था उसको अडॉप्ट कर रहे हैं हम. सीएलएस था, यू हैव द फर्स्ट सेंटेंस, देन सेप, द सेकंड सेंटेंस एंड देन सेप. अब ए और बी, इफ यू वांट टू डिटेक्ट वेदर दे आर पैराफ्रेजेस तो हम ए और बी देंगे दैट आर पैराफ्रेजेस, और सीएलएस टोकन को वन फोर्स करेंगे. सीएलएस टोकन का आउटपुट थ्रू द क्लासिफिकेशन हेड वन फोर्स करेंगे. ए और बी लेट्स से पैराफ्रेजेस नहीं है ट्रेनिंग डेटा सेट में, देन वी विल फोर्स इट टू बी जीरो. तो इस तरह आप डिफरेंट टू पेयर्स ऑफ सेंटेंसेस की प्रॉब्लम्स भी सॉल्व कर सकते हैं. एक तो पैराफ्रेज डिटेक्शन है, द अदर कुड बी trying to determine whether your sequence of sentences is coherently written. So let's say आपने पहला सेंटेंस दिया और दूसरा सेंटेंस दिया. If they are coherently written, it should output a one. If they are not coherent, meaning that second sentence does not follow immediately from the first sentence, then it should output a zero. मतलब sentence coherence या entailment आप भी निकाल सकते हैं. So just to, for example, let's say, so he studies at Lums. let's say एक ये सेंटेंस है, उसके बाद फॉलोइंग एक सेंटेंस आ गया, they went to KFC for dinner. So if they were the two sentences, obviously they don't seem to be coherent. One is on a different topic, the second is on a different topic. So for this would be an example of uh, the two sentences being incoherent, and it should output a zero, or the CLS for this pair of sentences should be zero. ठीक है, तो इस तरह आप अपनी एप्लीकेशन डेवलप कर सकते हैं. दे कैन बी अदर scenarios in which you can use this setting to predict whether two sentences uh, have. By the way, ये यहाँ हमने बाइनरी क्लासिफिकेशन की, इट कुड बी मल्टी क्लास एज वेल. कोई आप शेड्स निकाल सकते हैं दो sentences के, पहला सेंटेंस दूसरा सेंटेंस, क्लास लेबल्स कैन बी 1 2 3 4 एंड सो ऑन. सो इट्स अप टू योर इमेजिनेशन कि इसको आपने किस तरह यूज करना है. सो फॉर एग्जांपल आपने लोगों के पैराग्राफ, सॉरी आपने एसेज ग्रेड करने हैं. इफ देयर एन एसे इज पोorly written, obviously the first sentence and the second sentence की coherence कम होगी. So you can take a graded output, meaning like a continuous value from, let's say, 0 to 100 as a marking for this sentence कि ये correct अच्छा इसने लिखा हुआ है या अच्छा नहीं लिखा हुआ. Again, this would be possible if you have labeled data for it. आपको फाइन ट्यूनिंग करनी पड़ेगी. ठीक है, तो आपके पास उस तरह का लेबल थोड़ा सा डेटा है तो आप फाइन ट्यूनिंग करके वो प्रॉब्लम सॉल्व कर सकते हैं. सो ऐसे ग्रेडिंग फॉर एग्जांपल कैन बी डन एज वेल. ठीक है, okay, we are almost out of time, but I think we have covered almost all of this stuff. Let me just take a quick look. The sequence labeling एक टास्क है, वो हमने डिस्कस नहीं किया, वो probably next class में कर लेंगे. We'll introduce it and then discuss it. So there are two important tasks here, POS tagging and NER. So we will discuss that and then see how we can use a bidirectional transformer. You can also use a unidirectional transformer, causal transformer for this as well. So ये basically all for today है. So so we still have two quizzes left in this course. So I think I will take the next quiz after next week. Meaning that के ये next week मेरा बन रहा है next week बन रहा है मेरा 17 आई सॉरी नेक्स्ट वीक 10 है तो दैट 10 एंड देन 17 ठीक है 17 को फिर प्रॉब्ली आपका नेक्स्ट क्विज होगा एंड द फॉलो अप क्विज वुड बी ऑन 24 एंड नेक्स्ट वन वुड बी आई थिंक आइदर ऑन 1 और 2 तो फर्स्ट वीक ऑफ दिसंबर ठीक है तो दो क्विजेज आपके रह गए तो 17 एंड 1 ये जो 17 का क्विज है इट विल बी एन इम्पॉर्टेंट क्विज बिकॉज वी हैव कवर्ड a lot of important stuff here so I am giving you time to go over it and uh, prepare for the quiz ठीक है so in parallel of course आपका third assignment भी चल रही है there will be a fourth assignment as well and then of course a project as well so of course load थोड़ा सा है so try to manage that in an appropriate way if you need to take help from us so do come to me or the TAs तो आप assistance ले सकते हैं